Everyone, my name is S Maheshwara and I'm an educator at an academy. And you can follow me by downloading the Unacademy Learning app where you can find rest of my courses. And today we'll be discussing about the expression of the stagnation property. Also, you can rate, review and you can recommend this video to your friends, and you can also share this video. Also, you can follow our YouTube channel where you can find lots of amazing video and you can expand your knowledge base. So I'm looking forward to have a good discussion, guys. Have a good day.
Hello guys, and welcome back once again, and today we'll be discussing the lesson 9 of the topic of the compressible flow. And this lesson will be understanding the expression of the stagnation pressure, or we can say that we will be deriving this expression of the stagnation pressure. And my name is S Maheshwara, or being mechanical, and this is my short summary. So let's get on with it. So first we will understand what is the stagnation pressure. So what is a stagnation the pressure is that when a fluid is flowing past a body, so if we take this as a body and over here the fluid is flowing over it, then at a particular point the resultant force will be 0. So at this point the force is equal to 0, and this point is called as the stagnation point, because in this point the fluid is directly interacting with the surface, and at this particular point there is no deviation of the fluid. So at this point the fluid velocity will be equal to 0. So this point is called as the stagnation point. Also, the values of the pressure, the temperature and the density in this region are called as the stagnation properties. Yeah. So in this we'll be considering an adiabatic flow for the derivation. So in this the fluid is flowing like this, and it is flowing over the body, as we can see over here. Let ρ1 v1 and p1 be the density, pressure and volume at the section 1, and let p2 v2 and ρ2 be the corresponding values at the section 2. So we will be considering these two sections over here, and then let these be the respective values. So in this, basically what we'll do is that we will represent the pressure at this point, meaning the stagnation pressure, in terms of dc, or you can see it as m, where m is the Mach number. So we will be representing the pressure at the section 2 in terms of the m, which is the Mach number. So this is what we'll do in this derivation. So we will proceed with it. So first we will be using the Bernoulli's equation for an adiabatic flow. So this is the Bernoulli's equation for an adiabatic flow, as we all know. So in this, what we'll do first is that we will cancel the values of these, because they are common in both. And in this, the value of the z1 will be equal to z2, because they are on the same reference line. So if we take this as the reference, then these 2 points, they are in the same reference line, so we can cancel the value of z1 and z2. And after we cancel the values of these two z, we will cancel the value of the g's. So we'll be left with this equation. So we were left with this equation. So at stagnation point, the velocity v2 will be equal to 0. As we had discussed earlier, at this particular point, the velocity will be equal to 0. And let ps be the pressure at this section, and let the value of the ρs be the density value at the section. So ps and ρs are the pressure and the density at that stagnation point. So we can rearrange this equation as the value of this v2 will become equal to 0, and if you bring this value over here, we'll be getting this as the equation. So from this, what we are doing is that we will be moving this particular part over here. So after we move this part over here, and if we take the value of the p1 and ρ1 outside, so we'll be getting this as the equation. So in this, what we'll do now is that we will find the ratio of the ρ1 divided by ρs. So for a adiabatic flow, we know that p divided by 0 to the power of k is equal to constant. So what this means is that p1 divided by ρ1 to the power of k will be equal to ps divided by ρs to the power of k. So in this we can get the value of this ρ1 to the power of k over here, and we can bring the value of PS over here. So we'll be getting this as the equation. So if we take this whole to the power of 1 by k, we'll be getting the value of the rho 1 divided by rho s to be equal to P1 divided by PS to the power of 1 by k. So what we'll do is that in place of this, we will replace this value. So after we substitute the value, we'll be getting this as the equation. So we can write this as like this, as the PS divided by P1 to the power of T minus 1 by k. So if we, so now like what we can do is that we can add these two values. So after we add these two values, we'll be getting this as the equation. And in this, we will be moving like this particular part over here. So after the rearrangement, we are getting this as the equation. So now what we'll do is that you will like get like this whole value over here, and then we'll be shifting this value over here. So basically we are like trying to express this in a more simplified manner. So we are getting this as the equation, and we will mark it as 1. Now for a adiabatic process, the value of C is equal to root of K into R into T. Also, we can replace this RT by P divided by rho. So we can say that C is equal to the root of K into P divided by rho. Over here, C is the velocity of the sound wave. So therefore, at point 1, we'll be having C1 to be equal to the root of K into the P1 divided by rho 1. So if we take the value of C square, we'll be getting this as the value. So in this, as we can see, so now what we'll do is that this whole part is equal to this part. So we will replace this whole part by C square. So after we do the replacement, we'll be getting this as the equation, as you can see over here. And as we know that the value of M is equal to V square divided by C square. So over here we have like 1 V square, and we have over here 1 C square. So we can like replace these two values by 1 M. So we will be getting this as the equation after we simplify this. And this, as we know, M is equal to the V divided by C, where V is the velocity of the flow or like that particular object, and C is the velocity of sound, and this in the form of the V square divided by C square. So we can replace this value by M square. Now what we'll do is that we will represent the value of this PS divided by P1 in terms of this whole thing. So like what we'll do is that we will take this whole to the power of K divided by dk minus 1. So like this part will get cancelled, and this whole part of the equation will be having the power of K divided by dk minus 1. So the value of PS will be equal to P1 into this particular value. So we have this as the value of the PS, and where the PS is the stagnation pressure at that particular point, and the P1 is the pressure at the section 1 of the flow. Now if the value of this small v is like very small, meaning if the velocity of like that particular the flow, or you can say that like material is very very less, then the value of M also will be very less, because the value of this C will be very high. So as a whole, this value will be like less than 1. Hence this whole part of the equation, it can be represented in the form of the binomial equation. See, as the value of M is like very very small, then this whole value will also be very small, and since they are to the power of this value, so we can like easily represent them in the form of the binomial equation. So by binomial theorem, we'll be having PS is equal to P1 into this value whole divided by 1 factorial into this value, and then this value and the minus of 1, and this will become whole square divided by 2 factorial, and then we'll be having this part, and the next one will be like this part and the minus of 1, and the third part will be equal to this part and the minus of 2, and this whole will become equal to the cube, and this divided by 3 factorial, and this will keep on going on, and this is called as the binomial theorem of expansion. So in this, after we simplify this, we'll be getting this whole part to be equal to this, and this will go on till the value of the continuity. So in this, we can multiply the P1 from 1 and this part. So we have written is in this particular format. So in this, like what we'll do is that we will get this P1 over here, and then we will divide this whole part by P1. So we'll be getting this as the equation, and this will be equal to this. So in this also we can take the value of k divided by 2 into this m1 square as common. So after we take this value as common, we'll be getting this as the equation. And in this we can like express the form of m in terms of v and c. So we have done that. So we are like simplifying this particular equation. Yeah. And as we all know that the value of c is equal to k into the p1 divided by rho 1. Yeah. So we have substituted that, and now what will happen is that this rho will come on the top, and this k and this k will get cancelled. So after we simplify this, we'll be getting this as the equation. Now what we'll do is that we will cancel the value of this p1 and this p1. So we'll be having this as the equation. So we are getting this as the equation. So as we can see over here, if the value of m will keep on like increasing, then this whole equation will be like almost like equal to the 1 itself, because m is equal to v divided by c. So if the value of v is like very small, yeah, so if the value of the v divided by c is like very small, then this whole part will become like almost equal to 1 itself. So this whole part we will take it as 1 if the value of m is lesser than 1. Yeah, so this whole part will be like almost equal to 1. So therefore we will be having the value of the ps and the minus of p1 to be equal to half into rho into v1 square into 1. So we'll be having this as the relationship of the pressure. So in this, if we shift the value of this p1 over here, we'll be having the value of ps as this. So finally we have represented the value of the stagnation pressure ps in terms of the initial pressure and the initial density in this. And this is for the value of m to be lesser than 1. Now if the approaching velocity is very high, then m is like not a small value. So basically, if the value of v is greater than the value of c, then the value of m will be greater than 1. So we cannot like take this whole value to be equal to 1. So the simplified version of this equation will be equal to somewhat like this. So yeah, over here, since the value of m is greater than 1, then this value will keep on expanding, and by doing so we can find the value of the respective functions. Yeah, so guys, you know what, this derivation is a little bit big, so I will suggest you to pause the video and then go through it. Yeah, so these two are the values of the stagnation pressure equations for m to be like lesser than 1, and this is for the value of m to be greater than 1. So guys, if you are like any sort of doubt, then you can feel free to ask me. You can rate, review, and you can recommend, and also you can follow me. So in the end, I'd like to wish you luck, and I wish you to have a very productive day. Thank you.